We're going to talk about astronomical tools today. These are all tools that we use, or astronomers can use, to actually focus in on the universe around us. Our eyes are very important here on this planet, but when we look up in the sky, we see those itty-bitty, teeny-tiny, itsy-bitsy stars that up there in patterns. We have to wonder what they are. Telescopes or other tools have actually captured light from these far distant objects and transformed them into what we now know stars and the universe to be. So this is the first installment of Astro Tools. This one's going to actually talk a little bit about telescopes. It's going to talk a little bit about the electromagnetic spectrum or electromagnetic radiation, and it's going to start talking about spectra, which we determine with a spectroscope or a spectrometer. But basically, when we start these things, we have to start talking about why we use the tools, and I think I explained that already. And now, what is the function of these? And the main function of a telescope is not to magnify things. The main function is to actually collect, gather, and then focus light, so we can actually make the images to be what they really want to be. We do this in one of two ways. We either use a lens, and I should probably use this tool that I have just especially for this. We use a lens. This is called the objective lens, and the objective lens takes in these almost parallel light beams with a concave shape. It actually, if you think about this beam as having two sides, an upper part and a lower part, the lower part actually hits this glass first. Glass has a lower refractive index, and what it does, it bends the light down. Light here, it's the upper part that hits first, and that tends to bend the light up. And then it actually moves back and hits a focal point right there, and then the image is upside down, and it hits a mirror, and it reflects back and flips the image back the way it's supposed to be, and then it runs through the eyepiece. Now the eyepiece, like you can see down here, the secondary function of a telescope is to actually magnify the image, and that is usually done by this eyepiece. We can put in a 10x or a 100x or a 0.5x lens where we can actually make small things bigger or even big things smaller. But you can see the way this lens works, it actually flips the image back upside down. If you've ever looked through a telescope looking at like a tree or a distant object, and you wonder why it's upside down, it's because of this configuration. Okay, telescopes come in two different varieties. They come in what are called optical telescopes. Optical telescopes use visible light. They actually collect the visible light, and we can do that either with a refractor, a refracting telescope, or a reflector, a reflecting telescope. Or we have the non-opticals. If you don't really care if the object looks the way it's supposed to look, we can collect radio waves, we can collect infrared, we can collect ultraviolet, we can collect X-rays, we can collect gamma rays. This is a gamma ray telescope. Let me actually talk about these two first before we jump over here, because when we actually talk about this reflector, that's what the same type of technology these non-opticals use. But most of the telescopes you think of are the ones that actually collect the visible light. They're the optical, and again they're called refracting or refractors, or reflecting and reflectors. The objective lens is the most important part of the refractor. This lens has to be perfect all the way through. You want that light to pass through, and all the beams that are actually hitting it, even above this upper and below the lower and everywhere in between, you want all this light to go through, and with the shape of that lens to be perfect, you want it all to transfer through the glass, come through, focus in, and go through your eye. Now, why is a telescope so much better? If you want to think about telescopes, the main idea of a telescope is to collect light. The opening of this telescope collects as much light as your wallet and or technology can accept, but you're supposed to actually bend all this light so it can go right through that small opening, the iris of your eye. So what a telescope really does, it increases the eye size to be whatever the front of your telescope is. Okay, so you're collecting all this light. Refractor refracts or deflects the light, sends it into an image, and if the physics is all correct, you get a perfect image coming through your eyepiece. If you want to see something bigger, you just switch out eyepieces, put in a larger magnification. If you want to see it smaller, switch it out again and put in a smaller magnification eyepiece. Again, that's the secondary function of a telescope. Primary function is to collect the light. A reflector has an open end, that can actually have a piece of plastic there to keep dust from going in, but it has an open end, and its objective, or its primary purpose, is back here. This is a mirror. Now, you guys all know that a lens has to be perfect all the way through. You can't have bubbles, you can't have lint, you can't have anything if you want that light to go through. Back here, the only part of this lens or mirror that has to be perfect is that outer reflective barrier. You can do anything you want here. You can have tin cans, you can make it out of concrete, which could have anything in it. It can have nails, it can have screws, it can have bolts, it could have anything in it. Doesn't matter what's in the back. The only thing that's important for reflecting is that mirror. And it is called the reflector because the light, again, comes in parallel. It hits a concave mirror which bends the image inward. You can actually put your eye, if you watch these, the primary focus will be back here somewhere, or the focal point. But you don't want to put your head here because that blocks all the light trying to get in. So what you do is you put a mirror, and that redirects the light back up to eyepieces, and you can see the image does switch. So if you move that back over, that focal point's going to be about right there. But it changes the focal point's direction, runs through the lens, it magnifies it if you want to, and you can actually put your eye right there, making your eye think that it collects this much light. In a dark room, if you guys really don't want to turn on light to see things better, all you really have to do is imagine if your eye could be double, triple, quadruple the size it is, and it would actually get brighter and brighter and brighter. Okay, refractors use a lens to bend the light. Reflectors use the mirror to reflect it. Excuse me. The non-optical telescopes, if you take a look, the light comes in, hits a concave image. This is very much like the reflectors. Radio telescopes use reflected light. Excuse me. The light comes in, and you want to collect it again as much light as you possibly can. Primary purpose is to collect the light. You want to be able to have the right shape, and you can make this out of chicken wire. I actually had a radio telescope back when I was a kid that made it out of chicken wire. We actually fashioned it into a snow dish. Dish you use to jump down or to fly down hills. We actually fashioned it after that, and we actually bent the chicken wire more until we could actually collect it into a Radio Shack-like very simple collector, and from that we hooked up a speaker, and we could actually hear the static from the stars. But basically, you can make this out of any reflective object. You guys all know car antenna made out of wire. Doesn't have to be glass, doesn't have to be reflective like a mirror. All it has to do is reflect these waves. It's called the parabolic dish. It does have a receiver, and this receiver you can actually run a wire to a nice warm house, where this one you may actually have to stay outside where it's kind of cold. Gamma ray, same thing. It's got these reflectors. It is a concave shape. It bounces the gamma waves back up to this receiver, and then the receiver can, again, you can wire it to a computer hard drive and actually look at these images later in a different location. Secondary function of a telescope is to magnify the image, and that's usually done by the eyepiece. Okay, whether you've got a refractor, reflector, radio, or others, there are better places to put these things. Now, we know that radio telescopes, radio waves actually work 24/7. You can turn on a radio for a station or a TV, and you can actually watch these things 24/7. Doesn't really matter when you actually watch these. So for a radio telescope, gamma ray telescope, infrared, ultraviolet, and X-ray, it's not as important. But if you want a refractor and reflector, the best location is to put this thing up as far away from cities as you can. This is actually on the big island of Hawaii, out in the middle of the Pacific Ocean, the largest ocean, way high up above all the clouds, and you can see the cloud images there down below. So you don't get cloudy skies, you don't get as much atmosphere, you don't get artificial light, you won't get as much dust in the atmosphere. This is the best location for an optical telescope. This is the inside of the Keck's. The Keck telescopes are twins. You can get some idea of the size of this because these are vehicles down here. But if you take a look at it, they're fairly good-sized domes. Inside of it are very large mirrors, and I think you can see from the outside they actually are hexagonal mirrors put together, concave shape. It bounces up, and it's called a Cassegrain telescope reflector when the mirror is straight, and it bounces back down through a hole back here in this primary mirror, and the eyepiece would be right there. That's this kind of a telescope, and you can see it reflects up, hits this mirror right here, and bounces through that little hole, and then it actually goes down. And then you can see this area that's in between. This is the control room, where you can have lots of people, lots of computer hardware to collect, analyze the information. You can actually aim these two Keck telescopes to the same location, and what this does, it's not as well, it doesn't do it as well, but it tries to actually make an optical telescope that is as big as this is round. So the resolution's a little off, but with a computer you can actually make it think that it's a telescope that's that big, and that collects a lot more light, which again, primary purpose of a telescope, makes this telescope much more user-friendly. Okay, the bestest location, even if you can't get it up on a mountain, let's actually put it up in space. This is the Hubble Space Telescope, launched I think about 30 years ago. This telescope actually has been up there as a workhorse. It has a 3-meter reflector mirror back here, primary mirror. You can open this up, you can close it for dust. Not much dust, but there is dust up there. You can close this when you're not using it. It does have other pieces of apparatus. It's got communication, hearing and seeing for the planet, so you can actually get images, you can store them digitally, and then send them down to the Earth. Much higher than what this telescope, these Keck telescopes. Hubble Space Telescope can be 120, 130, 140, 160 miles up. So you can actually put this anywhere you want. There is no day or night. Problem with optical telescopes, daytime it's pretty tough, although these telescopes can actually focus in some things during the day. But daytime's tough, weather's tough, artificial light. This is the bestest location to actually put a telescope. 2014 James Webb Space Telescope. This is the Hubble Space Telescope, so the James Webb Space Telescope is supposed to be launched. It actually is supposed to be a larger mirror. I'm not exactly sure how large it's supposed to be, but it's going to see things even better than Hubble. I hope we can actually keep both of those up there because it's a cool thing to do. The electromagnetic spectrum. These are the waves, radio waves, the long end. And you can see they actually are traveling through space as waves, and they get closer and closer, they get more intense, frequency gets higher, the period gets, the number of waves per second gets more, the frequency gets more, the wavelength gets smaller, everything changes going this way. But we have radio waves, microwaves, infrared, visible, ultraviolet, X-ray and gamma ray. Gamma ray is really bad stuff, smaller than the atomic nuclei of an atom. They can go literally, they can go right through an atom, they can go right through a planet, they could go right through you. They get a little bit bigger, atomic size, molecule size, protozoan size, pinpoint of a needle, honeybee, human, building. They can even get as big as like the Earth. So these waves can get really huge. Frequency, you can notice this frequency actually looks like it's pretty good size, but it gets bigger going this direction, number of waves per meter, that's called hertz. And the temperature of the emitting body, radio waves are usually emitted by relatively cool astronomical objects, and the X-rays and gamma rays incredibly hot. Okay, they all travel through space as waves. How do they compare and contrast? They all travel through space as waves. They all have crests, top part of the wave, troughs, bottom part of the waves, wavelength from one crest to one crest, or one trough to one trough, and the period, the number of these crests or troughs or some part of the wave passing a certain location at one area. They all share that. They all, because they're all light, they all travel at the speed of light, 186,000 miles per second. That's more than 8 times around the world in 1 second. The only way they differ, and if you take a look at it, it's pretty easy to see, is the wavelength, how far there is between the waves. So a certain wavelength fits in this radio area, some of it fits inside this visible, some other fits inside gamma, and everywhere in between. One neat thing to think about here, the visible light, if you think about the infrared sight, this is actually saying this is more red than red. Red light is the longest wavelength color our eyes can see, and ultraviolet, even more violet than purple. Purple is the smallest wavelength we can see. Honeybees can actually make it a little farther into the infrared, and there are other organisms that see a little farther into the ultraviolet. This top part actually says, does it penetrate the Earth? Radio waves, yes. They start changing so that these don't, and then they change back in so these do, and then these pretty much don't get through. Our Earth does a really good job of protecting us from the things that are very dangerous. Okay, here's another view of the electromagnetic spectrum, or in this case electromagnetic radiation, giving you, again, the size. It's exactly opposite the way they've got it here. They've got radio waves here, and they're actually showing you we can use radio waves for radio. We can use microwaves for heating. We can use infrared for heat. We can use visible for seeing, ultraviolet for tanning, X-rays for actually seeing bones, and gamma rays, we can use those for actually producing energy if we can get enough of those. Okay, the next thing is, let's talk about spectra. The way you can actually make spectra is you break the white light, which usually comes from the sun, one reason clouds are white, and you break it up into its individual colors. The Roy G Biv, which stands for red, orange, yellow, green, blue, indigo, not really quite indigoic, or violet, not as purple as I would like to see, but there are the colors of the rainbow. Okay, here's an actual real rainbow. And how do rainbows happen? Rainbows happen when you have the sun. Actually, I've got a right about color here. When you have the sun behind you, you have rain in front of you, and if you get this certain angle, I want to say it's 105 degrees, but it looks like it's not quite that much. But you need to have a certain angle, so the sun usually has to be low in the sky. You don't get to see them very high. If you want to see one higher, go out, especially when the weather's warm, take your thumb, put it over the hose, and get a spray, and you can make a rainbow with that water. But you'll have to only be able to make it at a certain direction, so you may have to test it a little bit. But these are natural occurring rainbows. It does have to be sunny, you can see that. It does have to be raining, and you can see it. This is almost like really good, efficient virga. Virga actually is rain that falls into dry air and evaporates by the time it hits down, and I'm sure some of this looks a lot heavier up there than it is down here. You can see this is someplace out in the Midwest, nice flat area, probably not as much rain as we get here on the East Coast, but the way you get a rainbow is that the light comes in, it hits a water droplet. Okay, I like them as Mickey Mouse. They're drawing them here as a raindrop there. And it actually goes in. It does the same thing that telescopes do. It actually starts refracting the light. Red light actually starts bending out, and purple light bends out at a different time. And so it starts separating the individual colors, and then they actually get portrayed back down, and they hit you in the eye. So you get to see those colors. So if that rain moves farther away, the rainbow will actually get lower and lower in the sky till it disappears. If it gets closer to you, get higher and higher and higher till it's in the cloud, and then it doesn't get the raindrops. So it does have to be a very almost perfect situation to be able to see these. Okay, spectra. The way you get a spectra, you get starlight, you get a telescope, you focus the telescope through a spectroscope, and usually it has a triangular piece of glass or plastic. You can also have what's called a diffracting gradient. Diffracting gradient is a piece of plastic with 10,000 lines per inch scratched in, triangular lines, and they'll do sort of the same thing. But it'll break the light up into the individual colors. Now, we actually have black bands in here, and we'll talk about those in a second. Normally, you get what's called a nice continuous spectrum when you see these, but through stars, it starts giving these lines, and these lines actually tell us chemical composition. It's called the star's fingerprint. We'll talk about that in a second. Okay, anytime we get a hot, dense matter producing light, like a star, through this spectroscope, now they're actually showing you the diffracting gradient with all those little lines, scratches in them, you get what's called a continuous spectrum, Roy G. Biv, all the way across. If you get a hot gas, that emits light. Not so much high density, but more of a nebula, and it's called an illumination nebula, a light nebula. It's actually producing its own light, and you pass that through the spectroscope. What you get is what's called an emission spectra. It's emitting light, and you get the same colors, notice up there in the continuous spectrum, but you get them as bright bands. And these bands actually coincide with elements that are in that nebula. You can get what's called an absorption when you get that hot, dense matter going through a cold or a dark nebula. This will actually start absorbing some of the energy, and you actually see you get the continuous spectrum, but now you get those, instead of where the bright lines were in emission, you get dark lines in the absorption. Here is a spectra of a star, and you can see lots of bands. This is an absorption. Or this is a regular continuous spectrum with the lines that actually show, sort of like they are up there, resulting spectrum. And these are 4 of the 92 naturally occurring, 112, 114, including man-made of the periodic, 4 of them, where we actually take a piece of calcium metal and we actually get it hot enough where it starts glowing light. We look at it through a spectroscope, and these are the lines that actually identify calcium. It's called its fingerprint. There is no other element that has these lines. Hydrogen produces this set of lines. You see it's not quite as many. Iron produces this set, and magnesium produces this set. And if you take a look at it, these 4, there's nothing alike. They have that nice coloration, and now they flipped it from purple to red, the short wavelength to the long wavelength, but they actually have the same thing, except that these lines actually appear in different places. So here's an unknown star, and I'm going to ask you, what elements do you think are in this star? And all you have to do is go up there and compare them. Do you think magnesium looks like it's in that star? And if you take a look at that line right there, looks like there's one in that same location. Do you think iron is in the star? If you take a look at that dark line and that dark line with all the lines in between that dark line, those guys, do you see this in this star? I would tend to say yes. How about hydrogen with that line? Maybe. And how about that one? Nope. And what about calcium? We can go to the same area. There's nothing in the red in this unknown. There is lines of calcium in the red. For calcium to be in here, you'd have to see all these lines that are in there. Okay, so what elements are in that star? I would say iron is in that star. And of these 4, I would also say that magnesium is in that star. So we've got iron and magnesium in this unknown star. There are other things in there, maybe, but in terms of what we see here, and because they're actually showing you a known example, they only put iron and magnesium, but normally you would see lots of elements in there. But if you know what the spectra look like, you can get it. Okay, the last thing I want to show you, this is the Spectra of Gold, and we actually look at the spectra in 2 different ways. We see the continuous spectrum in the back with the dark lines. This is an absorption spectra. And we see the colored lines on a dark background. This is the emission spectra. Okay, and that's it for this one section. Appreciate you coming by. I am going to do version 2, where we'll actually talk a little bit more about spectra and what we can learn from it. But remember, we have 3 types of spectra. Spectra can make rainbows. It's actually the visible part of the electromagnetic spectrum. And best place to put a telescope is up in space. If you can't do that, you put it up in a high mountain someplace far away from cities, and then you decide what kind of a tool you want to use, whether it be an optical or non-optical. We tend to like pictures when they look the way they're supposed to. Opticals are very important, but astronomers now are leading more to here because they can do more of what a telescope is supposed to do, collect light. Okay, thank you much. Bye-bye. Look for version 2, part 2, coming soon.